Hello everyone, I'm Liu Jian, a graduate student from China, Beihang University. I'm honored to bring this report to you. The subject of my report is a wearable rest joint movement detection using two sensitive enhanced plastic optical fibers. The mainly studied that two kinds of POF sensors fabricated by different processing shown higher sensitivity to the rest movement than the conventional POF, and we use it to make wearable detection rest breaths. We have found that such sensors have great potential in wearable rehabilitation of human jets and other wearable fields. We submit our research results to IEEE Sensors Conference in June 2018. Among wearable devices, there is an increased demand for application for motion monitoring, virtual reality technology, rehabilitation, and mirroring the joint movement of human body. Devices used for this purpose are mechanical or electromechanical, which generally come into operation by using resistive tentometers or strain gauges. Compared to these electrical counterparts, fiber optic sensors are increasingly used for human joint angle monitoring because of its small size, lightweight, flexibility, and resistance to external electromagnetic interference. And the instruments that make up these systems are easy to miniaturize. Some studies have reported POF sensors based on intensity demodulation for mirroring the angle motion of labs. However, these conventional POF sensors usually demonstrate lower bending sensitivity. Therefore, in this study, we developed two POF sensors based on side processing that are more sensitive to angle change to monitor the movement of the rest during rehabilitation exercise. In this study, we used 3D printing technology to make two kinds of POF fiber clamps and fixed the conventional POF into a fixture to perform different side machining. The first step of processing is to insert the POF into the fixture shown in Figure A. The side graining using different sandpaper to obtain a D-shaped polishing zone and clean the residuals on the surface by ultrasonic device. The second step of processing is to arrange the POF in an arc-shaped groove fixture shown in this figure, and etch a periodic grating on the POF according to the structure of the fixture. After that, the manufactured POF sensor is embedded in a polyamide vest band to monitor the movement of human wrist. Human wrist detection motion can be decomposed into two basic directions, abduction, adduction, and flexion-extension. We divide these two directions as alpha and beta. To the best of our knowledge, the normal range of human wrist activities are about half about maximum range of motion in the alpha and beta direction. So we choose to detect activity in this smaller range. According to the detection characteristic of different sensors, the D-shaped POF sensor is placed on the back of the rest, and the etched grating POF sensors is placed on the side. The specific reason will be introduced later. By coupling the change in light intensity in two-way fibers, the bending angle of the rest in different direction can be demodulated. In order to verify the monitoring characteristic of the two sensors in actual rest joint motion, we designed an experiment. A semiconductor laser guided the light into the developed sensors through optocoupler. Then the power of transmit light was received by a photodetector with a conditioning amplifier. Finally, the output signal of sensor attached to the rest breath were fed into an oscilloscope to achieve the response characters. The reason for choosing this simple enhanced plastic transmission loss intensity demodulation scheme to detect human rest motion is the rest motion causes a magnified bending effect of the curvature change in the fiber. In the first step, we placed the conventional D-shaped and etched grating PUF sensors in the same position on the back of the rest. After that, the user wears the rest band to make a ARF direction motion, and the normalized light intensity signal is shown in the figure. It can be seen that the etched grating and the D-shaped PUF exhibit higher sensitivity than the conventional PUF, which is about 46.8 and 17.8 times of the latter. The etched grating PUF sensor exhibits a more pronounced change in the light loss due to a double change in demodulation expansion period and the effective refractive index. However, since the D-shaped PUF sensor achieves a better linear fit response, so it is placed at the back of the rest in consideration of the great angle extent of abduction and adduction motion. And the etched grating PUF sensor is placed on the side, according to the motion behavior of the rest joint. In the second step, we determined the final rest band schedule according to the above installation method to test the coarse intensity of D-shaped and etched grating PUF sensors to the rest joint motion. As shown in this figure, the D-shaped sensor has a better response sensitivity and a better linear fit to the abduction and adduction movement. It can be seen that the sensitivity to this motion is 0.0012 per degree and has a good linear fit, while the flexion and extension motion show a nonlinear behavior with a sensitivity of only 3 in 10,000 per degree. In contrast, the etched grating PUF sensors placed on the side of the rest, as this finger shows, it is more sensitivity to the flexion-extension motion, and with a good normalized sensitivity of 0.0071 per degree, and a better fit goodness in the above range. While the abduction and adduction movement show only a low sensitivity response of 1 in 10,000 per degree, and the linear performance was not good. In the third step, we designed a coordinate system based on the triangular relationship to virtually represent the bending angle of the rest joint. The angle alpha and beta, according to the horizontal and vertical coordinates, are respectively obtained by the developed sensors. And 0 degree means that the rest joint is in a stationary position. Then 8 random measurement points related on the composite motion of the rest are marked on the coordinates paper. And the user wears the rest joint sensors to sequentially trace the 8 mark points. The hollow points and the solid points mark respectively represent the reference and measurement data. And the area between them are shown in the table on the left. It can be said that the maximum absolute occurs alpha and beta occurs at the point 3. At the point 3, it's a minor 10 degree and 20 degree, which may be due to the large rest joint jitter. After the coarse area is removed according to the 3 sigma principle, the average error of the remaining 7 points is found to be 7.14 degree and 1.4 degree. This is tolerable compared to the generously accepted 5 degree motion evaluation performance known to us. That's all. Thank you.
Okay, thank you very much.